Alright, the Equation Slayer coming at you from a wonderful PD day by Miss Barnes. We made a video on similarity and right triangles. So we're going to learn about triangles and similarity. So let's start with this theorem. We have the altitude of hypotenuse, this guy right here. This is the altitude and it's going to the hypotenuse. And it comes perpendicularly. Of a right triangle forms two triangles that are similar to each other and the original. So this original triangle is similar to the two triangles that got broken apart by that altitude. So in fact, all three triangles, ABC, triangle ACD, and triangle CBD, the little guy, are all similar to each other. Alrighty. Now, the proof of this theorem is left as an exercise to the reader, so you can enjoy yourself with that. Any questions, ask Mr. Dobo. Give you a hint, you'll need the hypotenusal theorem. Alright, now to our first example. Write a similarity statement comparing the three triangles. So it's a good idea to kind of sketch the three triangles first, and kind of you want them all to be corresponding to each other. So if we take this big triangle, leave it alone, and then take the second biggest triangle and make it so that its hypotenuse is going to be kind of going in the same position as this hypotenuse. Its longest side is its shorter leg is going to be going vertical, and the longer leg is going horizontal. So same right here, make this small triangle so that PR is going straight up, PS is going horizontal, and this hypotenuse right here is coming straight up and down. So if we want to see what that looks like, we come right over here. And we get triangles RST, SPT, and RPS. And again, angle R is going to correspond with angle S, which of course corresponds with angle R. ST and T, SP, and P, all these angles are corresponding to each other. You could think of these three triangles as the Three Stooges, if you will. Someone once told me to think of them as Marley, Moe, and whatever his name is. Who remembers these three guys anyways? So, moving forward, example, dose. Consider this proportion right here. Everyone likes a nice fraction. Notice we have an x in this, alright? In this case, that means the proportions are of the same number, and that this is the geometric mean of the extremes. If we were to cross multiply this right here, let's just think about that. X times x is x squared. A times b is ab. We get this equation, x squared equals ab. If I want to solve for x, I just square root that, both sides, and I get x equals the square root of ab. So the geometric mean of two positive numbers is the positive square root of their product. So the geometric mean of a and b is the positive number x such that x equals the square root of a and b. So when we square root both sides, we don't have to worry about plus or minus the square root of ab. We're just looking at the positive one. And of course, this has to be positive because we're not taking no square root of no negatives in this class. That's for Algebra 2. So let's not spend a lot of time. This is a lot easier than it looks. What's a geometric mean between 2 and 8? 2 times 8 is 16. The square root of 16 is 4. Got a little lazy and just wrote square root. But 2 times 8 is 16. Square root that, you get 4. Now, what about the geometric mean between 4 and 5? Well, it's going to be somewhere between 4 and 5, and there's no whole numbers, so that'll be fun. 4 times 5 is 20. The square root of 20 is 2 times the square root of 5. And if you don't see why that is true, talk to your Algebra 1 teacher or see me after class, because this is geometry. And our last theorem here is... Oh, wait. Before I get to that, let's look at the Tom Brady of math, if you will. He kind of goes into a video explaining how to get these, take these geometric means that give us sides of a triangle, but there's this nice corollary that I was not aware of last year, and now I am. We have, if I want to find any of these lengths, I can just use these formulas right here. But instead of using these letters, I prefer these guys right down here. The altitude squared is equal to the product of this part times that part. If I want one of the leg squareds, for example, if I want this squared, this a squared, that's going to be x times this whole hypotenuse c. And if I want this leg squared, I'm just going to take y and multiply it by this whole length c here. Unfortunately, we're running out of time, so we won't be able to get some examples in, but don't worry. Another video is coming at you. Equation Slayer signing out. Thanks for listening. Subscribe, and thanks for listening.